Hello, everyone. Thanks for the organizers for inviting me to give this talk. So this is joint work with another Diego. So this is the outline of my talk. So let me start with the introduction and motivation. So Shantan also talked about convex IPs and conic IPs. So I have just a few slides summarizing my notation. So let's say that we have a convex set S, and we want to optimize a linear function over this set intersected with the integer points. So these problems are very important because you can model many interesting problems like this. But on the other hand, they are also difficult to solve. So one way you can approximate this is to solve the so-called continuous relaxation. So this will be a convex program, so hopefully you can solve it, right? But then two natural questions arise. If I solve the continuous relaxation and get the optimal point, let's say x hat, can I find a close by integer solution so that I can find a feasible solution for the convex IP as well? So this will be the proximity question we will try to answer. And there is a related question, which is the integrality gap. Can I find somehow the difference between the integer optimal value and the continuous optimal value? So obviously, if you can answer the first question, you can also answer the second question. All right, so what if we add more structure? Let's say we are not interested in only a convex set, but a conic set, conic representable set. Now, in this case, I introduce more notation. Let's say we have this U, which will be eventually the right-hand side. A is the matrix, and K be a regular cone, a closed convex pointed full-dimensional cone. And our convex set is now denoted by S sub U. As you can see, I am parameterizing the set with respect to the right-hand side U. And here the notation AX greater than or equal to K greater than or equal to U with respect to cone K means that AX minus U belongs to the cone K. All right, now we are still interested in solving a similar problem, but again, realize that I'm parameterizing the value function with respect to the right-hand side U now. And you can formulate many convex IPs as conic IPs. Some people believe that you can formulate all convex IPs as conic IPs using special cones. So these are very important subclasses. But on the other hand, they are difficult to solve again. So you can solve the continuous relaxation conic program now. Then you can repeat the same questions, the proximity and integrality gap question, but here the questions are a little bit different. So I want to answer these questions, if possible, whether I can answer them with respect to independence from the right-hand side, all right, the U vector. As I was alluding, so U is important and blah, blah. So why? You might ask, why are we interested in such an answer? So the motivation comes from Bill Cook and his co-authors' results from 1986, where they answered a similar question for linear integer programs. And they showed that they can bound the integrality gap independent from the right-hand side. And the bound depends on some parameter delta, which is a function of the matrix A, the objective function, and the number of variables. All right, so recently it has been refined by Joe Pat and his co-authors, and then there is also some related work recently. From the nonlinear side, there are also some. There's a list of work related to proximity results for different cases, but we haven't seen many results specialized to conic maps, so that's what we wanted to study with Diego. All right, so here's the summary of the talk. So I will talk about some negative kind of results and some more positive results. So on the negative front, we can easily find examples where the integrality gap is infinite. And for MISO-CPs, mixed integer second order cone programs, which is the first problem that may come to your mind when you are in the nonlinear world, or conic world at least. So integrality gap may actually depend on the right-hand side as opposed to Cook and his co-authors' result. And if you try to cheat and find the outer approximation of the Royans cone and then try to use the Cook results, you cannot cheat actually. So I will also talk a little bit about why it will not work, in the sense that you will not get a right-hand side independent bound. For the positive results, we show that if the recession cone of the feasible region of the continuous relaxation is full dimensional, then you can find some right-hand side independent bounds, both for proximity and integrality. And then we looked at simple SOCP sets, meaning sets defined by a single inequality, single second-order cone inequality. Then sometimes we get right-hand side dependent bounds, sometimes independent bounds. I will talk more about that in the later part of the talk. All right, so let me start with the negative results. I guess this is a very classical example. So even in linear integer MIPs, if you have irrational data, you can have infinite integrality gap. I think this is one of the first examples you may have seen in an integer programming course, I guess. But in our notation, you can even write it as a conic MIP, if you like, with nonlinear stuff involved. Okay, so here is an example from Diego, Chantonnay, and Juan Pablo's paper. Even if you have rational data, the moment you have nonlinearity, you cannot control integrality gap in general. And here is one example which shows that if you solve the continuous relaxation, you get minus infinity as the optimal value, but actually the integer problem has optimal value of 0. All right, so these are all sort of bad results, if you will. But then we have come up with more bad results in the following sense. So even if virtually very simple sets that you can think of, the bounds might depend on the right-hand side explicitly. So we have many examples, not only the ones listed here, but I will only focus on 2 for the sake of time. So let's look at a very simple, arguably the simplest, one of the simplest nonlinear sets you can think of, a parabola, and I'm intersecting with a half space, right? And I'm trying to optimize x2 here. So this is the picture. So the shaded area is the feasible region of the continuous relaxation. This point xz is the continuous optimal. And if you insist that the variables are integer, the best you can achieve is this solid point. And then you can compute the integrality gap exactly as this. And if you fix epsilon and change n, then as you can see, this goes to infinity. All right, so this is a fictitious example, of course, but you know, right-hand side dependence might show up for MISOCPs. So you may think that, well, maybe the unboundedness is the problem. Not really. So in this example, I have an ellipsoid intersected with a half space. Similar story. So the integrality gap becomes something like square root of n in this case, where n shows the radius of the circle here. Right, we have many more examples, so I will not go over each and every of them. And, you know, even more. So apparently, if you have 2 constraints, things go south, right? Right, how about cheating? And if we can find the outer approximation of the Lorentz cone, maybe then we can use Cook's results to get some bound. Well, first of all, to outer approximate the cone, you have to be careful. You have to use rational outer approximation because Cook's result assumes that. So I have a recent paper where I showed that a rational polyhedral outer approximation of the Lorentz cone can be achieved. Exactly the same complexity as Benton-Nemirovsky's approximation. So we can get a rational polyhedral outer approximation. But the issue is that outer approximation, also the Benton-Nemirovsky's approach, the constraint matrix of the linear inequalities, as well as the right-hand side, depends on the original right-hand side, right? So that's why you cannot cheat and do this trick, unfortunately. And actually we have, I have more slides as Chantonnay. So I have some details about why it doesn't work, but yeah. That's the thing. But later on, I will show you our type of results where you can get the bounds independent from the right-hand side for a feasible region like a circle, essentially, or a ball in higher dimension. All right, so these are all or some negative results. So let me then talk about more positive results. So unfortunately, you cannot say many general things. So one of the best results we could have achieved is based on this lemma, which is very intuitive, I guess. So let's say that we have this cone K, as in the picture, and I want to understand from the apex how much I need to move in the direction of an interior direction from the recession cone so that I can fit a large enough ball. Because if I can manage that, and if I choose the ball large enough, it will for sure certainly contain integer points, and I can answer the proximity question, and similarly the integrality gap question. And then the step that will for sure take you to a large enough ball depends on, of course, how large you want the ball to be, and then some parameter of the cone, right? Now, from here, maybe it's not so obvious, but the point I want to make here is that the apex doesn't play a role in this analysis. Therefore, even if I move around the cone, if I translate the cone, the same theta bound, theta parameter will be valid. Okay, so what is the use of this? Well, what then we can say is that let's talk about the set S, a translated cone with the apex x hat. Then we can answer the proximity question as this, where you can see that x hat doesn't show up. So it's x hat independent, somehow it's right-hand side independent. And once you have a proximity results, you get the integrality gap result for free. So it's also x hat independent. So I explained this from the translated cone perspective, but actually, whenever your feasible region has a full dimensional recession cone, you can play the same game, and you can get bounds independent from exactly where the continuous relaxation optimal point is. Okay. Now, in the rest of the talk, I will focus more on so-called simple SOCP sets. And this is the reason. Unfortunately, we couldn't get many more results for general conic MIPs or convex MIPs. And you may remember that for SOCPs, even two constraints are not that good. So that leaves us the only option of looking at simple sets defined by a single SOCP constraints. All right, so here we will specialize our analysis to ellipsoids, paraboloids, hyperboloids. These are the only possibilities, in addition to translated cones, I guess. And then I will talk about two approaches to get bounds. The first one is the proximity-driven approach, and then we have the integrality gap-driven approach. I will talk more about them later on. Okay, so what's the definition of a simple SOC set? Well, as you may guess, it is just one Lorentz cone type of constraint, right? And if you don't like the norm, you can take squares of both sides and get what I will call as the QR representation, standing for the quadratic representation. But one thing is important, you may need to keep the linear inequality, so that might be important. So I will comment on that later on. All right, so assuming that the linearity space is trivial, then the analysis boils down to understanding this matrix and the eigenvalues of this matrix. If this matrix is positive definite, you end up with an ellipsoid. If you have a single zero eigenvalue, you end up with a paraboloid. And if you have one negative eigenvalue, you have a hyperboloid. Such a matrix cannot have more than one negative eigenvalue. So this is enough to look at. All right, so perhaps this is an obvious result. So if you give me this set, and if you tell me that it is non-empty and bounded, actually it's an ellipsoid. And we can show that it's an ellipsoid. In this case, you can drop the linear inequality. And you can write this set as a truly ellipsoid-looking set. What do I mean by this? This is constant now. It doesn't depend on the variable x. And there's a tedious formula that does it for us. Right, so I will denote this by ER, ellipsoid representation. I will be referring to this later on. Okay, some more preliminary notation and definitions. This is the set which is called the lattice. So if you have a Q matrix, which is for rank, then you look at Q times Z vectors, where Z's are the integers. So that defines a lattice. And for a lattice, you can talk about the so-called covering radius. So you can think about the covering radius. I think I have a picture here as follows. You look at the continuous point and then the closest integer point. You quantify the distance, and then you take the worst case. What is the largest distance from a continuous point to the integer point in the worst case? So here on the picture, you see some ellipsoids, and this ellipsoid for sure contains some integer points. However you move it around R2, for sure you will contain integer points. And you can show that the covering radius in this case is square root of 5/2, for instance. And the nice property of covering radius is that if your R is large enough, then for sure this set will contain integer points. So this is a step towards answering the proximity question. All right, now I think we are ready to move on to our approach. The first approach is so-called proximity. So the idea is very simple. So we solve the continuous relaxation, let's say, and get X set. And then I want to fit a large enough ball in the feasible region, which is close to X set. If I can achieve this, then perhaps I can quantify the proximity measure. All right, so I will show you how our results look like. So this is a table which shows in which cases you can get what type of bounds. So it turns out that for ellipsoids, for which all three representations are possible, you can get right-hand side independent bounds, just like Cook and his co-authors. For hyperboloid, you can also get right-hand side independent bound. But unfortunately, for paraboloid, even if you have no additional constraints, you might have the integrality gap depending on the right-hand side. Right? I think that was a bit surprising to us. In general, under some additional conditions, you can get rid of the dependency from the right-hand side. So all these representations are equivalent, so I will just pick one of them for each of these cases and show you the results. All right. Okay, for ellipsoids, the results look like this. I mean, you don't need to, understand everything necessarily, but the important thing here is that I give you an ellipsoid in this form, and then the result says that, well, you can get a proximity measure like this, which depends on Q, the matrix, and RQ, which is the covering radius of the lattice defined by Q, and it doesn't depend on anything else, in particular P or R. All right. Again, so this is as close as we can get to Cook type of results, and whenever you have a proximity result, you can get an integrality gap result for free. For instance, you can use Cauchy-Schwarz inequality to get this. But in this case, if you are a little bit more careful, you can improve the bound from here to here. I mean, what's the difference? You take alpha inside. So it's a little bit better. All right, so for paraboloid, actually this is a proposition which is more general. But here we are looking at a set S, which is unbounded, but defined by a quadratic. So potentially this is non-convex. And a parabola can be written like this, by the way. And then if you give me a point on the boundary of this set, again, showing the continuous relaxation in mind, keeping the continuous relaxation in mind, we can get a proximity measure, which looks like this, square root of n, the dimension, plus this delta problem, which is another hard-looking optimization problem. Right, so if you can solve this problem, you can get delta and find a proximity bound. As you can imagine, this explicitly depends on the right-hand side because all the problem parameters are here, right? Of course, you can question this approach. Maybe there's a better one, right? So that is possible. But if you're interested, I can also show you the example later on. We have an example in which a single parabolate, but integrality gap depending on the right-hand side explicitly. So even if this may not be the optimal approach, still you cannot beat it. A good result is kind of, positive result is that if the head, which is the tangent, has a large norm, then you can get rid of the dependence of everything, essentially. And that's kind of intuitive, because think about the parabola. If you are near the apex, so you may not fit a ball. But think about the parabola and going way above, then it's much easier to fit a ball. So that's kind of the intuition. And maybe I will skip this slide. So this just shows that you can also bound the integrality gap using a similar technique. For hyperbolate, the result is somehow nice because you can show that for hyperbolate, the recession cone is actually full dimensional. Therefore, we can use the result from the general conic MIPs and apply it here. So that's why you can get a right-hand side independent bound for free. All right, so this is the proximity-driven approach, and this is the summary. If you want to keep one thing in mind, you can keep this in mind. And then the next approach is the integrality gap-driven approach. So for the proximity, we were trying to answer the proximity question first, and then go to the integrality gap. So here, we are just directly going to answer the integrality gap approach. And what is the idea? Well, first of all, I will make some simplifying assumption that I'm optimizing in the last component, which you can always do if your original objective function is integer. And then here's the idea. So let's say that, again, x hat is the continuous optimal. So you draw the tangent here. And then you move this hyperplane into the feasible region until the hyperplane intersected with the set is large enough. If it is large enough, then you can find integer points in this intersection. Now, the important thing is that this set S delta turns out to be an ellipsoid in the lower dimensional space. Therefore, you can easily analyze it. So that's the main idea. And this analysis is a little bit more general. So you can get both right-hand side independent and dependent bounds, as I will show you in a minute. Right? So this is a horrible-looking technical proposition we will need. So it turns out that, so let me show you, this S delta can be written very explicitly as this ellipsoid times the level that you are at. And this radius of the ellipsoid is a quadratic function of the delta value, the level that you choose. And the coefficients of this quadratic function can be explicitly written like this. Again, you don't need to memorize, of course. But the important thing is that Q2, the coefficient of the quadratic term, is right-hand side independent. And the other two are right-hand side dependent. So you will show in the bounds which one plays a role. All right, for ellipsoid, there are two regimes. Now we are in the QR representation because it's much easier to analyze this case with the quadratic inequality. There are two regimes in the ellipsoid, for the ellipsoid case. In the first regime, you get a bound which is right-hand side dependent because all these Q0s and Q1s show up. Actually, the proof is sort of easy, although the expressions look tedious. And you can play with this and get a right-hand side independent bound as well. In the second regime, as you can see, the expression is even uglier, but you can still get right-hand side independent bound. The interesting thing is that the right-hand side independent bounds depend on the regime, which regime you are at. Okay. All right. For parabolates, the bound looks very nice. It's just like this. But it depends on the right-hand side because Q1, if you remember, was right-hand side dependent. And for hyperbolate, again, we get right-hand side dependent and independent bounds. And again, this is the summary of the type of results we get from the integrality gap-driven approach. So you may ask, okay, which approach is better, so to speak? So here, let me illustrate this with two examples. So here is an ellipsoid. And in this case, you can solve the continuous relaxation and the integer problem in closed form. So that's nice. So that we can quantify the integrality gap exactly. And then if you use the first approach, which gives you a right-hand side independent bound only, it gives you something like this. As you can see, as n goes to infinity, it converges, but it depends on how fast it does that. For the second approach, integrality gap, if you look at the right-hand side independent bound, they are actually the same. So in one of the regimes, they turn out to be the same for this particular example. But if you remember, the second approach also gives you right-hand side dependent bounds, in which, in this case, they actually match the exact integrality gap. So there's this relationship. All right. So here is the second example. I know that there are so many terms, but the only difference between this optimization problem and the other one is that the right-hand side is changed slightly. So this is a smaller, so to speak, ellipsoid. And then you can again solve the continuous relaxation and the integer problem explicitly. And the right-hand side independent bound for the proximity-driven approach is unchanged, which should be the case because it doesn't depend on the right-hand side, right? But for integrality gap-driven approach, now the regime is different. Therefore, the bound that you get is different. And for the right-hand side dependent bound, you get some horrible expression like this. But what we can show is that, as you might expect, the right-hand side dependent bound is the best one because it uses more information somehow. But the first approach actually gives you a strictly better, actually this is strict, better bound than the right-hand side independent bound of the integrality gap-driven approach. So that's why I think both approaches have some certain meaning to it. All right, so that's mostly what I want to say. So we have some results for non-simple SOCP sets as well. For instance, the intersection of two spheres. We know from our counterexamples that we cannot get rid of the dependence from the right-hand side, but still we can quantify in some cases what would be the integrality gap in this case. And some of the results do not necessarily use the SOC structure. So perhaps we can extend some of them to more specialized cases. For instance, mixed integer SDPs, mixed integer exponential column programs, etc. Right, so I think that's all I want to say. Thanks for listening.